Hello Chem students, we're going to look at chapter 5 material. That's the chain conformations, where we're looking at staggered and eclipsed conformations, calculating delta H's and energy tables, and calculating K equilibrium. So we have two types of organic groups that we're going to work on conformations. One is chains that are on a straight line. We can rotate around any single bond 360 degrees. And our next chapter, chapter 6, we'll look at cyclohexanes. We'll look at different chair conformations and a boat conformation. Okay, so these changes in energy for these conformational changes are very low, usually well under 20 kcals. For just a rotation around a single bond like this, it might be 3, 4, 5 kilocalories. And so they can go on very easily at room temperature and usually are occurring thousands of times per second. Okay. So single bonds can rotate through 360 degrees, and the energy changes as it does that. So we'll see something called staggered and eclipsed, and there's many conformations in between that we just ignore. A typical single bond rotation would be down here around 3, 4, or 5 kcals. In our world, we have much more energy. We have about 20 kcals background energy, and so things that require less than 20 can happen just from the energy in the background world that we have. If anything required more than 20 kcals, we might have to do something like heat it up, or sometimes you can do things photochemically that have higher energy values. One way to think about the energy is to think about a cost that you have to pay or money that you get. So I often use this analogy of 20 kilocalories is the same as 20,000 little calories. And look at each little calorie as $1, so that would be like $20,000. So if you have $20,000 to spend, that's our background energy, and you had to buy something that costs $4,000, you could easily do that. And so we can easily rotate through these different conformational changes. However, if you had to buy something that cost $25,000, you'd be stuck. You wouldn't be able to do that without borrowing some money or doing something extra, saving it. Now, in organic structures, we have many types of molecules and many types of shapes. So I just picked here our C5H12 examples of structural isomers. So we have a straight chain, pentane, or we have a 4-carbon chain with a 2-methyl butane. Or we have a 3-carbon chain, propane, with 2 methyls, so 2,2-dimethyl propane. And around any single bond here we can rotate. And that's what we're going to look at for this particular topic. Now the whole molecule can rotate, but that's more complicated than we can handle. So we're just going to look at a single bond at a time, and then assume that we can extrapolate from that in terms of our thinking. Computers can do more extensive calculations on the whole molecule. So what we're going to do is we're going to start with a real simple molecule, ethane, which only has 2 carbons. And this could be written many ways. We could write a condensed formula like this. Doesn't tell us much, but really there's only one way this could be drawn. We could write it like this, which is a little more informative. Shows 2 methyls connected by this bond. We could write it as a 2D Lewis structure, where we can see all the bonds and we can see the connections between the 2 carbons. Or we could write it as a 3D structure, something like this one right here. As a 3D structure, we can rotate this bond around. We'll have many other shapes that are possible. This is one that we're going to study here called staggered. But say we rotated a little bit so that we rotated one of these guys up so it was facing this hydrogen on the left. We would call this one eclipsed, and it has a different energy, a higher energy, which we're going to see. Now the way we're going to look at these is with a Newman projection, which is very useful for allowing us to see the interactions between the bonds on the front and the bonds on the back. And so what we'll do is we'll sight down the 2 atoms that we're talking about. I usually draw myself a little eyeball looking straight at the front one towards the back one. And we're going to draw these in a certain symbolic way. We're going to make the front one just a little dot. We're going to make the back one a big circle, which isn't really the way an artist would do it. An artist would make the front one bigger, but then that would hide the back one, and we have to see that. So we're going to do that. Now, we won't see this bond because it's behind the dot, but we will see the other 3 bonds. They will be a little bit unnatural from what we're thinking. These are tipping out at 109-degree bond angles. but when we look at them straight on, they'll look flat, and they'll divide up a circle into 3 equal wedges, which appears to be 120 degree angles. But remember, they're tilted out towards you, and in the back they're tilted away from you. So our front dot is going to have these 3 bonds, and the way I have it shown is I have one sort of straight down, one up and to the left, and one up and to the right. So straight down, up to the left, up to the right. These are on the front carbon. And then we'll have 3 bonds in the back. Okay? But in the back, you'll notice that the bond that's straight up and down, it's up. And so it's going to split the difference between the 2 on the sides here. We call this staggered, so it's in between. And if I put in the other bonds in the back, they will also be in between, staggered. So this is a good way to draw the staggered conformation. I tend to draw them all the same. I mean, you can draw it staggered many ways, but I tend to always draw it the same because we're going to look at rotations through 360 degrees, and you want to try to keep as much as possible the same viewing perspective so that you don't get mixed up. Okay, so we're going to leave the back guy always straight up and to the left and to the right. Okay, now if we add in what's on ethane, it's very simple because all of the other bonds, all the bonds are to a hydrogen. So all the way around, all 6 positions are hydrogen. We're going to look at more complicated molecules as we go through this, but initially this just tells us we filled in the blanks, the 6 blanks, 3 on the front with hydrogen, 3 on the back with hydrogen. Okay, so there's our staggered conformation. And now if you have models, it's really helpful to look at models for this particular topic. I don't have them shown here, but this would be very helpful for you to do that. Okay, so just take 2 methyls, stick them together, and start rotating them around to see what your possibilities are. So again, this is called a Newman projection, looking at the front towards the back. We don't see the bond behind, but we see the 3 bonds in the front and the 3 bonds in the back. All right, so here's our first Newman projection we drew. This is a staggered one with the groups in between. And then what we're going to do is we're going to take the front group and rotate it 60 degrees. So this hydrogen that's in between will come up and be on top of the hydrogen in the back. And this hydrogen on the right will rotate down on top of the hydrogen in the back. And this hydrogen on the bottom will rotate up to the left to this on top of this hydrogen here. Now we're not going to draw them exactly on top, the front groups exactly on top of the back groups, because then we couldn't see them. We want to see both groups that are here. So I slightly misdraw them. Notice I went a little bit past on this guy, and a little bit past on this guy, and a little bit past on this guy, and I can see all the hydrogens on top of one another, which we call eclipsed. Okay, so this is an eclipsing conformation, and this is a staggered conformation. As we rotate through, we have what's called a dihedral angle. So any particular reference point in the back compared to a reference point in the front. And I just picked these 2 hydrogens that were straight up and straight down. The angle between them, if we circle around there, is called the dihedral angle. So this first example here would be a 180 degree dihedral angle. If I rotated it 60 degrees, it would be a 120 dihedral angle. And if I rotated another 60 degrees, that would be a 60 degree dihedral angle. And if I rotated another 60 degrees, it would be a 0 degree dihedral angle. These would be eclipsed. Okay? So that's a common term that's used, just to give you a reference point there. Now, if I took ethane and I rotated, I'm going to make a little reference point here with the squares. So start off here with a square on the bottom in the front, and a square hydrogen in the back. And then I'm going to rotate this front guy through 360 degrees all the way down the line. I'm going to get a lot of repeats, okay, because they're all hydrogen. So first I have staggered, 0 degree rotation, but then I'm going to rotate 60. Okay, so I rotate 60, I come to an eclipse conformation from the staggered. So now I have groups on the top, groups on the front carbon right on top of groups in the back carbon. I rotate another 60, and I'm at staggered again. The same equal energy to what I had at the start, but we're referencing this one hydrogen. So we just keep rotating all the way through. We'll have a staggered eclipse, staggered eclipse, staggered eclipse, and finally I get to 360, which is right where I started over here. Okay, so that's kind of repetitive. Now, we're going to say that the eclipse conformation is higher in energy, and we're going to say that's due to the repulsion in the sigma bonds on the front and the back carbons being right in each other's face. So the electrons are closest here when they are eclipsed. Now it's really more complicated than that, but that's the argument we're going to use. So I have electrons repelling electrons on the top here, I have that in the front, and I have that in the back. All right? So this is higher energy because of that electron-electron repulsion. Now if I rotated 60 degrees, I would have the electrons over here. It's a little bit farther away, so we would say the electron-electron repulsion is a little less, and the energy would be a little lower, and this would be a little more stable. Okay, that's going to be our argument. But like I said, it's a little more complicated. If we looked at these other factors that we're ignoring, if I have the eclipse conformation, I also have repulsion of the nuclei. So I have a hydrogen here repelling a hydrogen here that are closer together, and so that would be higher energy, just like we saw up here with the electrons. But on the other hand, if I rotate them eclipsed, the nuclei here are closer to the electrons in the other sigma bond, and the nuclei here are closer to the electrons here, and that would be an attractive force, which would lower the energy. So it would be hard for us to make those estimates, but computations and so forth have shown that the eclipsed is less stable, and so we're just going to assume that the electron-electron repulsion here is the deciding factor. Okay. So now we're going to look at the energy changes that occur. So I'm doing exactly the same thing. I'm just making a little reference point with this ball on the front and this ball on the back in the vertical directions. And I'm going to rotate this through 360 degrees. So we just saw that the staggered conformational energy is lower, and then as we go to the eclipsing conformation, the energy goes up. So I'm just going to give to you that the energy between these two is about 2.9 kcals. We're going to call it 3, okay? Because if it's 3, since I have 3 of these, 1, 2, 3, we can attribute 1.0 kcals to each of these eclipsing interactions of a hydrogen with a hydrogen. We're going to build up a little table of energies so that we can calculate the energy of other molecules, the conformational energy. Now if I rotate staggered, I go back down to 0, and eclipse back up to about 3, and so forth. So that's just a very simple, repetitive energy change going on and on. When we are in the eclipse conformation, there's a special term they use to describe that. The eclipsing conformation, the energy of eclipse, is called torsional strain. Molecule's a little strained because we're raising its energy. And so as soon as we go staggered, then the torsional strain is lowered. It's a little more stable. Okay. So torsional strain is something related to what we call steric effects. Okay, steric effects, I just say it's due to electrons in bonds of one group being close to electrons in bonds of another group, and another way of saying that is big groups get in the way of each other. All right, so that's going to be a repulsion, that's going to raise the energy, and there's many ways we could do this. This is one of our big 3 arguments in organic chemistry, steric effects. Okay, so we have greater steric effects or torsional strain in this particular eclipsing conformation. Now the other main arguments that we use in organic chemistry are inductive effects, and inductive effects is a shift of electron density in a bond towards either towards or donating, or away from or withdrawing through a specific site in a sigma bond. Okay, it's based on electronegativity, so something that's more electronegative will attract electrons to itself, and something that is less electronegative will give up its electron density a little bit. So I always say it's sort of like a tug of war between 2 atoms, and the one that's more electronegative will attract more of the electron density, leading to an imbalance. We might call it a dipole, where there's a partial negative and a partial positive. A second very important argument in organic and biochemistry is resonance effects. So resonance effects, we talked about those in another video, in another chapter. This is delocalization of electron density through parallel 2p orbitals. So this could be in pi bonds, or could be in lone pairs of electrons that are right adjacent to pi bonds. Okay, that's the way the electrons can move through the 2p orbitals. So this is probably one of the more complicated things to see in organic and biochemistry, is the resonance effects. And then the last one, we're just beginning to see our first example, steric effects. Like I said, large groups get in the way of one another, and that's basically based on repulsion of electron clouds. Okay, so now, since we have an energy difference, we could calculate an equilibrium distribution between our two conformations. So I have over here staggered, and we know that's lower energy. And then we know we go up about 2.9 kcals to eclipsed, that's higher energy. And so we could calculate how much of each of these we have if we make some assumptions. So our assumption is going to be that delta G is the same as delta S. We're going to assume that delta G is the same as delta H. We're going to assume that T delta S is small compared to delta H. So that's a common assumption. It's not always true, but at room temperature is oftentimes true. Right? So then we can come down here and use this equation. The equilibrium constant is equal to 10 to a power. The power is the energy change that we're talking about. So in this case, that'll be 2.9 kcals divided by 2.3 RT. 2.3 is a number. R is an energy constant that we're going to call 2 calories per mole per degree Kelvin. And the temperature, we're just going to say is about room temperature. So I assumed here 298, or you might say 300 degrees Kelvin. So if we multiply this whole thing out here on the bottom with 298, it comes out to about 1,380 little calories, which I'm going to call 1,400 little calories. And then we have our energy term on the top, which is 2,900 little calories. And so we'd have 2,900 over around 1,400. So that comes out 10 to the minus 2.12. You could punch that in your calculator and get a number. So I have 1 over 130. Because we're going uphill in energy, we have less of the higher energy form. We only have 1 versus 130 of the lower energy form, based on the 2.9 kcal per mole energy difference. If we turned it around, we would be at the high energy, and we would come down to the low energy, so we're thinking that should be a bigger number than 1. And we would do the same thing. Now we have a minus 2.9. So if I come down here and put a minus, this would be a plus number. And so I would get a number bigger than 1, 10 to the 2.12. And so I would get 130 of the product, which is the lower energy form, and only 1 of the starting material. So again, we could look at this in terms of money, in terms of this difference right here, $2,900, or you could look at it in terms of elevation. So this would be a mountain. We could say it's like 2,900 feet tall. If you're on a bike, you would have to pedal your way up there, do a lot of work to get to the top. But if you were on a bike and the mountain, if you're at the top, you could just pick up your feet and coast down to the bottom. It would be spontaneous. Okay, so you could look at it different ways. Those are a couple ways that I look at it. Okay, we're going to make our Newman projection a little more complicated now. We're going to add in another carbon. So now instead of ethane, we have propane. We still have to look down 2 attached carbons. Okay, so I have here this bolded line to tell me that I'm looking at between 1 and 2. Okay, and this will be one of the groups on 2. Now I could either look to the front or I can look from the back. And so we have more perspectives now. Okay, so I could look at the front, and the front would have 3 hydrogens. Or I could look toward the front from the back one, and I would have 2 hydrogens and a methyl. So these are 2 ways I could draw it. The way that I would probably draw it myself is I would look 1 to 2, and then that methyl would be in the back. Since it's the biggest group on the number 2 carbon, I put it straight up at the top. Now this is still super easy Newman projection, because that's the only different group. Everything else is hydrogen. Okay, so this is the way we're going to look at it, 1 to 2. So then we have to put the 3 groups on the front, those are all hydrogens, and the 3 groups on the back, 2 hydrogens and a methyl. Since I always have you start with the lowest energy conformation, it'll have to be staggered. Okay, so again, it's just a repetitive equal energy change going on and on. So I'm staggered. We reference that to 0. Okay, it's not actually 0, but that's our reference point. And then when we rotate to eclipsed, the energy goes up to 3.4 kcals. That's a little higher than we just saw with the 2.9 kcals. Okay, so there's a reason for that. That's the methyl is a bigger group. So there's more electron-electron repulsion in the staggered conformation. How much more, how much energy is that going to cost us? Well, we can figure it out now, because we just figured out that hydrogen facing hydrogen was 1.0, and hydrogen facing hydrogen is 1.0, so that's 2. If this whole thing is 3.4, that means the hydrogen facing the methyl must be 1.4. So now we have a little bit bigger table of energy. We'll keep expanding that. So now we have 2 terms. We can do a little more complicated calculations if we wanted to. Okay. Now we can also do calculation of the equilibrium constants. So here's the one that we just did with ethane. So remember, that was 130, the lower one, and 1 of the higher one based on the 2.9 kcals. But now our energy difference, okay, K equals 10 to the minus whatever that energy difference is over the background thermal energy, which we're calling about 1,400 kilocalories per mole. And this is 3,400. Since we're going uphill, it's a positive value. So we have a negative of a positive. It's going to be a negative exponent. So I get 10 to the minus 2.48. Notice the equilibrium distribution is there's more discrepancy here. We only have 1 out of 303 because the energy difference is larger. So now I have 302 in the lower energy, staggered, and only 1 in the eclipsed conformation. Now remember, this is not a static distribution. These guys are changing back and forth tens of thousands of times per second. But if you took an instantaneous picture, you'd find most of your molecules staggered and just a little bit eclipsed. Okay, and there'd be a little bit more, a little bit less staggered here because the energy difference is smaller. All right. Now we're going to make our molecule a little bit more complicated. We're going to put on a second carbon, add a second carbon. So now we have 4 carbons in a row, butane. We have more perspectives now because we could look 1 to 2 or 2 to 1. Or we could look 2 to 3, which would be equal to 3 to 2, either way. And so we're going to do the more interesting view, which is in the middle right here. Okay? So I have all the different perspectives here. You can take a look. If I look at C1 first, I have 3 hydrogens. But if I look at C2 first, then I have that ethyl group, okay, on the front. But if I look in the middle, okay, I have 2 hydrogens and a methyl and 2 hydrogens and a methyl. So either way we look at it, it's 2 hydrogens and a methyl. So if we look, say, 2 to 3, and I put always the biggest group in the back straight up. And then if I have a big group in the front, I put it as far away from the group in the big group in the back so that it is in this shape here. We call that anti. We'll see that in just a minute. Okay, so that's going to be our starting point, always at the lowest energy. Now I have all the possible Newman conformations shown here. We just have to fill in the blank. The important one is the first one, because that's the one that's going to determine all the others. We're going to leave the back carbon the same all the way across, and then we're going to take this first one and move it 60 degrees at a time until we go all the way around for 360 degrees. Okay? And then at each of these places, we're going to calculate some energies as our table builds up. So I give myself a line of sight. This is what I do for myself. I put a bold bond in between the 2 that I'm looking at. I put a little arrow pointing in the direction I'm going, and I put an eyeball here to mean I want my mind to actually view this particular perspective. Okay. So we have to fill in the details. So the front details are there's a methyl and 2 hydrogens, and the back details are there's a methyl and 2 hydrogens. Since I want to start with the lowest energy conformation first, I put the biggest group on the bottom and on the front carbon, and the biggest group on the back carbon at the top. So these are as far apart as they can get because they're big groups. And that's our 0 reference point. Now if I rotate up, we don't really know the energy of this one, but we could calculate because we just figured out a couple of energies. I have a hydrogen facing hydrogen, that should be about 1. And I have a hydrogen facing a methyl, that should be about 1.4, and another one 1.4. So that should add up to 3.8. Okay, if we come down and look at this, this is very close to 3.8. And then you might remember that this was really a little bit smaller than 1, but we just called it 1. So that could be the discrepancy right there, but it's very close to what we would predict. Now if I rotate the methyl again, I'm back to staggered. So you might think, oh, well, we were staggered over here, it must be the same. But notice the difference. Big group on the top, as far away as we can get big group on the bottom, staggered. But now when I go to staggered, I have the big group staggered close to another big group. So staggered is better than eclipsed, but this isn't perfect here. This isn't as good as we have over here. We don't know this energy, so I have to give that to you. That's going to be 0.8. Okay, we're going to call this gauche, this particular conformation. We'll call gauche. Okay, now if I rotate another 60 degrees, I come into a bigger problem. Okay, I've got one kcal here and one kcal here, but I have two metals facing each other, and that's going to be more steric repulsion. The energy for the whole thing is 4.5. So that must mean that since we have one here and one here, these two metals eclipsing each other cost us 2.5. Okay, so that's not going to be a very favorable conformation, but it's just rotating through to the next one. So I come over here and I have another gauche. Okay, again, it's off to the side and staggered like we had over here. So I'm thinking that should be around 0.8. And then I rotate again so that the metal and the metal are facing hydrogens. This should be about 3.7. Then finally I rotate back to anti, and this should be back down to our 0 reference point. So you can see this is a more complicated energy picture. We're going up and down, but not always the same energy. There's little differences in there. Okay, so our table's a little bigger now. We could look at a hydrogen facing a hydrogen, 1.0, a hydrogen facing a methyl, 1.4, and a methyl facing a methyl, 2.5. Okay, we're going to expand that energy table even beyond that. But first, let's do a little calculation. First, let's just go over those energies that I just gave you. 1.0 for HH, 1.4 for H carbon methyl, and 2.5 for two methyls facing each other. We have some complicated terms. I'm going to give them to you, but we're going to go with the simpler terms that people typically use. So in these conformations, if both groups are above, say, this horizontal line, okay, they're on the same side, we call that, this is our reference group, we call that sin. So the second group is sin to this reference group because it's on the same side of if we cut the circle in half. Okay, if we're below the halfway line to the reference group, we call that anti. So these are terms: sin on the same side, anti on opposite sides. Now another thing that we look at is how close are they to planar. So if they're both within this little X region right here, vertical up and down, we call that periplanar. Okay, periplanar. And if we rotate this group down here to the middle region over here, sort of off to the side, could be 90 degrees or something close to that, we call that clinal. So this gives rise to the actual technically correct terms that we don't really use, but I'm just giving them to you. So our terms are going to be anti when these are far apart in the plane together. This one we don't really use a name. We don't have any common name for this. If they're close together, the larger groups are close together, or any group is close together, 60 degrees and staggered, we call that gauche, or you might say gauche. Either way, I say gauche. And if the two groups are eclipsing each other, whatever they might be, we call that sin. So if we come down here, remember this is anti, and they're both in the same plane, so the proper term would be anti-periplanar. These two are anti because they're on opposite sides if I look at that horizontal line, but it's sloping away. I think that's a geology term. So this is clinal, anticlinal. If I move this up above the line, but still sloping away, that's synclinal. And if I move them up into the same plane, but on the same side, we call that sin periplanar. So we just take the sin out of this one. We take the gauche, a totally different name, gauche, and then we call this anti. And then we never really refer to that one. Anything else that's in between, some other strange angle that we're not really talking about, is called skewed. So those are skewed conformations, but we won't actually use that term for our lesson here. Now there's something that went on there that you probably weren't aware of. I'm just going to point it out because we're going to come to this same topic in Chapter 7 in stereochemistry. Now something you are aware of is your two hands. If you hold your hands up and face each other, you'll see that they're mirror images. However, you know they're different because you've lived your whole life with your hands, and the right hand is not the same as the left hand. Okay, so you have that personal experience that tells you that. Now, if I hold the two molecules that are in the eclipsing conformation that I've shown here, you can see they are mirror images of each other. Two hydrogens, H and methyl, H and methyl. Okay, so these are mirror images. But if I slid this one across, they would not be superimposable. So they're just like your hands. They're different. When mirror images are different, we have a special name called enantiomers. So these would be enantiomers, which are different mirror images. Again, we're going to come to that in Chapter 7, so don't worry about it right now. That would also be true for the Gauss conformations. So here I have Gauss on the left, and here I have Gauss on the right. They look really similar, and their energies are identical. However, they're not exactly the same. It's like your hands. So again, these are enantiomers, which are chiral conformations. Chiral comes from Greek. It's a Greek word for hand. Now there's another kind of strain that we had in the butane which I ignored, and I will continue to ignore that. But that is when I have a big group up here, it can get in each other's way. The electrons can repel each other through space separately from the sigma bonds that are down here. The sigma bond eclipsing interactions down here are called torsional strain. However, these groups up here are also in each other's way, and these are called van der Waals strain. So if I had the groups kind of far apart from each other, not close, there would be no strain problem. But if the groups are tilted in towards each other and they share some common space, that's going to produce a lot of repulsion. That's going to raise the energy and make it less populated to have that particular shape. Okay, that's called van der Waals strain. So let's take a look at a new molecule, and then we're going to try and calculate all these energies. Excuse me. Okay, and this is our little energy table that we have. All right, and so first we have to decide how to draw our Newman projection. Well, what am I saying? I'm saying use C2C3. Okay, the name I wrote here is 2,3-dimethylbutane. So what I would do is write out 4 carbons for the butane, and then at the 2 and 3 positions put a methyl group. Okay, so that would be our molecule. Now I'm looking at 2 towards 3, so I look at 2, and what I see is 2 methyls and an H. And when I look back at 3, I see 2 methyls and an H. So I'm going to try and put the biggest group on the back on the top and the biggest group on the front on the bottom. And so those are going to be the methyl groups. Okay, so I have 2 of them, but I can just put 1 of them down. So I'm going to do that. Then the second methyl I'm going to put on the front here, I have to put it Gauss, so the methyl in the back. On either side it would be Gauss, so I put it over here. Now here's where we have to make a decision, because I have another methyl group in the back, and so where do I want to put it? Do I want to put it over here on the left, or do I want to put it over here on the right? And so if I put it over here on the right, hopefully you can see I'm going to have more problems, because I'll have a Gauss, and a Gauss. But if I put it over here on the left, I'll only have a Gauss here and a Gauss here. That should be lower energy. So I'm going to put it on the lower left here. All right. If I had put it over here, just to remind you, I'd have 3 Gauss interactions, and that's going to be higher energy than 2 Gauss interactions. Remember, Gauss interactions are 0.8 for methyls. So then I just fill in the 2 hydrogens at the end, and this would be our starting structure. We would begin with this. Anything is going to be, any rotations, is going to be higher energy forms. So I start here. Now I add up these energies, I got a 0.8 and a 0.8. So relative to no strain at all, I'm going to be 1.6 above our 0 reference point. Now if I rotate to eclipse, I'm going to rotate this up here 60 degrees. So I have a carbon, methyl versus a hydrogen, methyl versus a hydrogen, methyl versus a methyl. We know all of those energies. So we add those up, 2.5 plus 1.4 plus 1.4. We come out with 5.3 kcals, higher, quite a bit higher, you can see. Now if I rotate staggered, okay, I have some Gauss interactions. I have 1, 2, 3 of those. 3 of those is going to be 2.4, and you can see that's why we didn't use that one here, because this is only 1.6. So it's much lower, but still higher than our starting one. Now if I rotate again, I'm going to have 2 methyl eclipsing interactions. That's going to be 5. Plus I have the 1 kcal per mole of the 2 hydrogens. That's going to be 6.0 altogether. So this is higher energy than this eclipsed conformation over here. So I go down 2.4, back to the one with 3 gauge. I go up where it's eclipsing again, and then I go back down to our starting point, and we just repeat that over and over. So again, you can see it goes up and down, a little bit different each time. But this is how we could calculate the energy for this, knowing the stuff that we just learned. Right? So this is the way we're going to do it in our course. I'm going to give you these energies. Now, some of them are real and some of them I made up. I just did my best guess as far as the interactions. So we know that eclipsing interactions are higher energy. And I'm going to look at these possible groups. So I could have hydrogen and hydrogen, or methyl, ethyls, isopropyls, T-butyls, phenols, and a bromine. Okay, and they can interact with any of these up here. For gauge interactions, those are generally a little smaller because remember they're farther apart. But I have those same groups that are possible: hydrogen, methyl, ethyl, isopropyl, T-butyl, phenyl, and bromine. Notice how I use abbreviations for these. We're not going to want to write out all these structures in full detail because it makes it very difficult to write all the conformations. So we just use these little symbolic symbols for their names. And don't forget our little equation. Ek equilibrium equals 10 to whatever the energy change is divided by 2.3 RT. Now we're going to have 3 groups in the front and we're going to have 3 groups in the back. So if we just number around here, 1, 2, 3, 4, 5, 6, you see we have 6 total positions to fill in from the groups that are up here. That means at each position I have 7 possibilities, and 7 possibilities, and 7 possibilities. So the total number of possible structures I could give would be 6 to the 7th. Okay, 6 positions with 7 possibilities. That turns out to be quite a big number, about 280,000. So you can't really memorize a particular problem, the answer for it. You just have to figure it out each time. But the approach is exactly the same each time. So that's the approach we're going to do. So our problem that we're going to use as an example wants us to calculate the relative conformational energies of all these conformations of this compound. So 2-methyl, 3, 1-methyl ethyl, 4-phenyl hexane. So you would have to be able to draw the structure. Got to know a little nomenclature. I would start down here at the end. Hexane is 6 carbons. And then I would start at the 2, I have a methyl. And at the 3 position, right next door, I have a more complicated substituent, a 1-methyl ethyl. Okay? Now you might not be able to visualize that, but that is the same as an isopropyl. So, and then at the 4 position, I have a phenyl, so you'd have to know, that's an aromatic ring. So our structure would look something like this. 2, we have a methyl. 3, we have a 1-methyl ethyl, which is the same as isopropyl. 4, we have a phenyl, and then we finish off the molecule. Now I'm going to say that we need to draw C3 to C4. So we would have to find that C3 carbon. That's where we're looking first. That's going to be our dot. And then we draw towards C4. They have to be attached. Draw towards C4. So I usually bold that bond in so I can see what are the groups on the front and what are the groups on the back. Now there's one little detail that you might overlook, and that is we do not show the hydrogens. This is the bond line formula. So when I look at the front carbon, I only see 2 groups. There's a 3rd group that's a hydrogen on this C3. And when I look to the back, I only see 2 groups. So there's a 3rd group that's a hydrogen. So we're going to have to put those into our Newman projection. So remember, we always pick the biggest group on the front to point down, and the biggest group on the back to point up. If they're both the same size, you just pick one of them and make it the bottom group. Okay. So here's our perspective, and notice I'm going to change the symbols of these. I'm not going to write out all those carbons. I'm going to put isopropyl, IPR, and same over here. And of course I have a hydrogen. And in the back I'll write pH for phenyl, and these 2 carbons right here would be an ethyl. So I can take all these guys and make it a lot easier to draw into the Newman projections. Okay. So we start with the lowest energy 1. We're going to put the biggest group, I would say that's a phenyl, straight up on the back. And then isopropyl, put that straight down on the front. Okay? And then we're going to add in the other groups. Now remember, we have to worry about gauge interactions, so we want to try to minimize those. Now what I would do first is I would fill in the back one. So I put a phenyl, put the ethyl on either side that you want, say ethyl and hydrogen, but then fill that in all the way across. You're not going to change that back perspective. You're only going to change the front perspective 60 degrees at a time. Okay. So here I have all the back positions filled in. Right. Now I take the big group, the isopropyl, I put it down, and then I have to put in another isopropyl and an H. I don't want to put the isopropyl over here because it would be 3 gauche interactions. So instead I put it on the left. I have a gauche here and a gauche here. That's 2 gauche interactions. So that's our starting energy right there. I'm going to rotate 60 degrees at a time, so I'll go to eclipsed. That'll be much higher energy. And then I'll rotate staggered. That'll be lower. And then I'll rotate eclipse. That'll be higher energy. Then I'll rotate lower. That'll be staggered, lower energy. And again, eclipse and back to the starting point. Okay. So we're going to have to figure out interactions at each point along the way from our little tables that we have. So here's our tables. Okay, this is eclipsing energy values, and this is gauche energy values. So initially we started off low, meaning all gauche. So I have 6 of these. I have one here, one here, one here, one here, one here, one here. So I just calculated them around 1, 2, 3, 4, 5, 6. And eclipsing, I only have 3 calculations because there's just eclipsing on the top and on each side right here. So there's more work on the staggered. Those will be lower energies. And then less work here, but higher energies. So let's take a look at what that is. So if I look at phenyl H, come up here and look at H, go over to phenyl, looks like 0.2. So I'm going to bring that number right here. If I look at H versus ethyl is 0.1. Ethyl's a little smaller group, so I'll bring that right here. And if I look at ethyl versus isopropyl, I'm thinking this is going to be a little bigger. Okay, so I find ethyl, I go over to isopropyl, I see 1.6. Okay, and then if I look at isopropyl versus H, H versus isopropyl 0.2, and H versus isopropyl again 0.2, and now this one's going to be big. Isopropyl and phenyl would be 2.1. Okay, if we add all that up, it comes out to 4.4. So the energy cost for this particular conformation has a starting value of 4.4. Now we're going to go to the eclipsing energy table and start off with the top one, which is phenyl versus isopropyl. This is probably pretty big. Isopropyl and phenyl is 8.1, so that's going to be quite large. Okay, there we go, 8.1. And then if I look at H versus ethyl, probably not too much, 1.5. So a little bit bigger than a methyl, 1.5. And then the next one is isopropyl versus an H. H versus isopropyl, that's a little bit bigger, 1.6. So if we add all those up, it comes out to 11.2, and you can see it is quite a bit larger than the staggered conformation, okay, because it's eclipsed. Now if I go to staggered, I would do that all over again. So you can check me on my work here. The phenyl versus isopropyl, phenyl, isopropyl 2.1, and then you can check going down, see if I did that right. But you can see this staggered is higher than our starting staggered because there's 3 gauche interactions, whereas there's only 2 over here. If I rotate to eclipsed again, okay, I'm going to have a big isopropyl and phenyl, and a big ethyl and an isopropyl. So that's going to be quite large. Okay, and then I have a hydrogen-hydrogen, we know that's 1.0. So this, in fact, is the highest energy conformation. Okay, and then if I rotate to staggered again, so I have a gauche interaction here, phenyl isopropyl, I think we said that's 2.1, and then isopropyl ethyl, that's 1.6, and then isopropyl ethyl, 1.6, isopropyl H, 0.2, HH we said was 0, okay, and then H phenyl, we said that's 0.2. So this is 5.7. So not quite the same as the staggered conformation here. And then we go to an eclipse. I'll let you take a look at that. Just check it up in the table over here. And then we come back to where we started, 4.4. So you can see this is a much more complicated energy picture. None of them are the same. They're all different. But it's definitely an up and down based on staggered versus eclipse, staggered versus eclipse, staggered versus eclipse, and staggered again. How big they are depends on how close the big groups are to one another. Okay, So hopefully this will help you be able to do the problem. The problem that we do on the test is going to be very similar to the one that I just went through here. And if you can do this and understand it, you should do well on the test. As far as calculating, what I usually have you do is take the lowest energy one and compare it to the highest energy one and use that energy difference. In this case, that would be 9,200 little calories, 9.2 kcals. So that's on the top. I have 10 to that number divided by 1,400. That comes out 10 to the minus 6.6, so that's going to be in the millions. So that's about one of these guys up here for every 4 million of these guys. So you can see there's not much up here, but remember, they're rotating through all of these different conformations tens of thousands of times per second.